Hello, welcome to today's lecture on deep learning. Today we will go back to deep learning after this short detour in Nadaraya-Watson regression and look at different attention scoring functions that are typically used in deep learning and multi-head attention. So the most commonly used attention scoring function is the Softmax attention that we already met. Now, what does Softmax attention do? Well, it takes our database of keys, combines it with the query to compute this attention scoring function little a, then applies a softmax to it, and then builds a weighted average of the output of this softmax, of all of these a's, with the values that correspond to the keys. So this might be K1 here, this here is V1, up to Kn, Vn. And now you're computing a weighted average over the values where the weights are based on the attention weights. So the outputs of the attention scoring function that is brought to a value between 0 and 1 using the softmax. And all of these weighted values are then added together to compute the output of the softmax attention layer as this weighted average. The nice thing about using the softmax is that it ensures that all attention weights are non-negative. And the nice thing about using very simple functions for A as the attention scoring functions is that this can be computed very efficiently on a computer. Now, many of these distance-based kernels that we have looked at in the context of Nadaraya-Watson regression are relatively hard to compute. But let's look at why relatively simple functions such as just the dot product between the key and the value might be appropriate. So remember that the Gaussian kernel is the exponent of minus 1/2 times the squared norm of the difference between the query and the key. Usually you would have also this x-pair of A, but that we ignore right now. Let's just look at this squared norm. This squared norm between the difference of the query and key, if it is the Euclidean norm, can be written as the inner product between the query and the key minus 1/2 the squared norm of the key minus 1/2 the squared norm of the query. So we have the inner product minus a term that depends only on the key and minus a term that depends only on the query. Now let's look at these terms. Well, typically we use the same query for all our keys. Yeah, we are performing query to the whole database. So actually the norm of this query is always the same. So when we remember that we're comparing attention between different keys, so we're basically computing here a term that is identical, and thus in order to compare them would be irrelevant, especially if we normalize the attention weights then to 1, this term would disappear completely. Similarly, we have this term that is based on the norm of the keys only. Well, there are many reasons to say, well, that the norms of those keys will also be quite similar for different keys. And there are also different operations that we commonly apply in deep learning, namely batch normalization or layer normalization, that actually make these often constant. Yeah? So they are very similar to each other, and thus they can usually also be removed. So if these two are in practice usually irrelevant, well, what is left then? Well, what is left is only the inner product between queries and keys. Thus, this might be a good way to do attention scoring, and actually inner products, so dot products between vectors, are highly efficiently computed in GPUs. So these are quite suited for deep learning. Now, of course, we want this inner product to be relatively independent from the number of dimensions of these queries and keys. So if we assume that this inner product for each dimension has the same standard deviation, then if we divide by the square root of the number of dimensions, then we would achieve that the standard deviation of this whole inner product would stay constant, so would not increase or decrease as we're increasing the number of dimensions. So the so-called scaled dot product attention function is defined as the inner product between the query and the key divided by the square root of the number of dimensions. Now, we said that we're usually using Softmax attention so we would take our attention scoring function a, little a, and plug it into the Softmax in order to achieve non-negative attention weights. So attention weights alpha would be the Softmax of a between q and k, where a is just a simple scaled dot product. So in the end, putting it all together, what we would get is the Softmax of these, which would be e to the power of the dot product between the query and the key, divided by the square root of the number of dimensions d, and this whole thing divided by the sum over all of these exponentiated dot products to normalize the values to lie between 0 and 1 and to add to 1. And that, of course, is already quite similar to the Gaussian kernel, where we basically have left out these additional terms that depend only on the norm of q and k. A typical application for deep learning models is sequence models, and especially attention is often applied to sequence models. Now, if we deal with sequence models, we have to be a bit careful because sequences might be of different lengths. For example, we might have a sequence of 1, 2, 3, 4 tokens. We might have another sequence of 3 tokens and another sequence that only contains 2 tokens. And during training, they might all end up in the same mini batch. Of course, we want to still be able to process them together. So we have to be able to modify our softmax observations to deal with the fact that these sequences are of different lengths. So a trick to do that is by first introducing some dummy tokens, basically blank tokens, to all the shorter sequences, such that all the sequences are then on the same length. Now, of course, when you're now computing your attention, you don't want these blanks to affect the attention. Yeah. So we do not want blank in our attention model, but we want somehow to be able still to compute all of these things together. So a trick to do that is to limit the weighted sum over all of those attention weights times the values only to the first L terms, where L is the actual sequence length. So for this here, L might be 2, and that means that we ignore these two blank terms. Here L would be 3, and here L would be equal to our total N of 4. So in deep learning, we also want to achieve that we can always compute these operations using tensor multiplies by batching computations together and parallelizing them on a GPU. So how can we do that for our dot product attention? Well, we want to be able to compute the attention score between many queries. So we might have a query tensor that has n A times B query matrices and apply this to a key tensor that is of dimensions n times B times C. Then we can use batch matrix multiplication to compute these element-wise products. So batch matrix multiplication would then compute the n element-wise products. So we would compute an inner product over the joint dimensionality. In this case, B here would compute n different query key output matrices that are now of size A times C. So if we have defined batch matrix multiplication in this way, we can in one go and easily to parallelize compute the attention weights for n queries that are each of dimensionality D and m keys that are of the same dimensionality, and that would give us our Q times K transpose divided by the number of dimension D square rooted plugged into the softmax. So the result of that would be n times m. And now if we have the corresponding m values, then we can weigh each of those values by the corresponding attention between the query, each query and the keys. And this weighted average is built by a matrix multiply to compute this resulting matrix that has n different query outputs times the number of dimensions of the values. Now, one assumption of the scaled dot product attention, the way we've written it here, is that the queries and the keys have the same dimensionality. Otherwise, we cannot compute this matrix multiplication between Q and K transpose. What can we do if queries and keys may have different dimensions? One thing that we can do in order to deal with this mismatch is to introduce a matrix that is of the size of the number of dimensions of the query times the number of dimensions of the size of the key, so the number of dimensions of each key. And then instead of computing Q transpose times K, we compute Q transpose times M, where M is this, so to say, adapter matrix times K. An alternative that we could also do is to just use, instead of a dot product, to use an additive function. So additive attention scoring works as follows. Well, we have two different weight matrices. One weight matrix that is only applied to the queries, and another weight matrix that is only applied to the keys. And then we compute the inner product between the weights and the queries and add that to the inner product of the weights times the keys. So these two weight matrices need to have one dimension in common, but the second dimension can be different. So the number of queries dimensions of the query could be q, and the number of dimensions of the key could be k. But after this multiplication of each of those, so each of those terms would then have dimension h, and they would be identical, so we can add them now up and apply this element-wise then h function to bring them to the range of -1 to 1, and then multiply another weight vector to the result of that. Now here we have introduced several learnable parameters, namely the entries of this matrix Q, the entries of the matrix WK, and of course the entries of this vector WV that weighs in the h different dimensions of the output. Now this little a is our additive attention scoring function, and if we want to make those non-negative and normalized, then we can apply the softmax element-wise to this whole vector. Now we know how to compute different scoring functions. Now, sometimes you might want to be able to use the same queries, keys, and values to combine them in different ways, but using the same attention mechanism. So you might have some trained parameters in your attention layer, but you might want to modify your queries and keys a little bit and then apply attention to it. And this is the goal of multi-head attention. Multi-head attention uses a number of fully connected layers that are each linear to create many different projection of the queries, the keys, and the values. You started out with just one set of queries, one set of keys, and one set of values. Now you have h of these transformed query, key, and value. And now you take these transformed q, k, and v to compute attention. You don't do that just once, but you apply the same attention layer now to those h differently transformed query, key, and values. And that computes you different forms of these attention layer outputs, which are different weighted average of these transformed values. And you put them all into one vector that concatenates everything. And you reduce that to a manageable size using a single fully connected layer. So the output of each attention is called a head, an attention head. So you have h many of these heads that applies basically the same attention operation, just to different linearly transformed query, keys, and values. We've already looked at the image. Now let's write down the formulas. They're quite simple, so don't be afraid of them. So you have a query, vector q, then a key and a corresponding value. Now, for each of these different heads, we are first computing a linear transformation, then attention, and then we pool all of these heads. So what we're computing in each head is hi. It's a function of a weight matrix applied to the queries, a weight matrix applied to the keys, a weight matrix applied to the values. So we call these weight matrices WQ and index them by I, where I is the index of the head. So we have H many of these WQs, WKs, and WVs. You multiply them to the corresponding query, key, and value vector, which gives you a linear transformation of this vector. Now you're computing your function f, and f is your attention pooling operation. So f is always the same function, but the input to f are these differently transformed queries, keys, and values that are transformed using these different W matrices. But f could be any of the attention functions that we got to know, for example, additive attention or the scaled dot product attention. And now the output is computed as the weighted or the linear transformation of all of these concatenated H attention heads. So each of these attention heads is our HI, which has some form of dimensionality, and we are transforming it using a weight matrix WO in order to compute an output vector of dimensionality R to the PO. So let's summarize this lecture on attention scoring functions and multi-head attention. We introduced two key attention scoring functions, namely the dot product attention and additive attention and variants thereof. And these can be used to aggregate even across sequences that have variable length, using this trick that we stop the aggregation in our sum after L steps, where L is the actual length of the sequence. Even though we have computed the attention scoring function with some dummy variables. The dot product is computed very efficiently, and it's actually also the main building block of modern transformer architectures that we will learn more about later. And we have seen that using either an adapter matrix, we can compute the dot product attention for queries and keys of different length, or we can just revert to additive attention that doesn't require a dot product of two vectors that have the same length. Now, computing or being able to compute attention efficiently is extremely important in deep learning. In fact, optimizing these sorts of attention layers has been a key area of advance in recent times. So NVIDIA has brought up a great transformer library, and they have also developed this Megatron attention mechanisms for building large language models with billions of parameters. And finally, we have seen that multi-head attention combines knowledge of the same attention pooling mechanism, but it applies it to differently formed query, key, and value combinations, where each of those head would then be concatenated together and in the end would be plugged into a linear transformation to compute the output of the multi-head attention. So with this overview, I want to say goodbye for today and see you next time. Bye bye.